Netflix, serving over 200 million subscribers, faces a critical challenge: optimizing content delivery to minimize buffering and ensure a seamless viewing experience. Buffering leads to a 30% drop-off rate, costing millions in lost viewership. We'll architect a food delivery platform, drawing parallels to Netflix's content delivery network, to drastically cut abandonment and boost efficiency. By the end, you'll design a system handling millions of concurrent users while improving delivery times. We'll revisit that 40% abandonment rate and show how our design directly tackles it. Here's what most engineers get wrong: they underestimate the impact of real-time logistics on user attention. Let's define the scope of our food delivery platform. Functionally, we need user authentication for both customers and drivers, restaurant management for menu updates, order placement, real-time location tracking of drivers and orders, secure payment processing via a payment gateway, push notifications to keep users informed, a matching algorithm to efficiently pair drivers with orders, delivery driver management tools, comprehensive order management, search functionality for restaurants and dishes, and ratings/reviews for both restaurants and drivers. Non-functionally, we need low latency for a responsive user experience, high availability to ensure the system is always accessible, eventual consistency for ratings and reviews, and strong consistency for order status to prevent errors. We also need to consider edge cases. How do we handle surge pricing during peak hours or inclement weather? What about reconciliation of payments between users, restaurants, and drivers to prevent fraud? Here's the twist: the system must also handle promotions and discounts, which adds another layer of complexity to the order processing and payment calculations. Now, let's estimate the scale of our DoorDash-like platform. Assume 1 million daily active users. If 10% place an order daily, that's 100,000 orders. If each order averages 5 API calls, search, menu, place order, payment, confirm, that's 500,000 requests per day, or roughly 6 QPS at peak. Each order might require 1 kilobyte of metadata storage. 100,000 orders times 1 kilobyte equals 100 megabytes per day. Over a year, that's about 36 gigabytes. For bandwidth, assume 10 location updates per minute per driver, each 100 bytes. With 10,000 drivers, that's 10,000 times 10 times 100 bytes equals 10 megabytes per minute. Keep this in mind for the scaling section. The secret is understanding how these numbers impact our architectural choices. This is where most engineers fail to plan adequately for geospatial data storage and retrieval, leading to performance bottlenecks. Remember this, it comes back later when we discuss sharding strategies. With the requirements and scale defined, let's design the high-level architecture for our food delivery platform. We'll separate read and write paths for optimization. The write path handles order placement and updates, while the read path serves real-time location data and restaurant information. Here's where most engineers make a critical mistake. They don't separate these concerns. This leads to read contention and slow performance. Remember the 40% abandonment rate? Let's avoid that. We use Kafka for asynchronous tasks because it provides ordering guarantees and allows for replayability in case of failures. SQS was considered, but it lacks these features. The system needs to be fast and responsive. We'll expose an API endpoint like post/API/v1/orders, restaurant ID, items array, delivery address, which returns order ID, estimated delivery time. This API is crucial for mobile app integration. We also need an API gateway to handle authentication, rate limiting, and request routing. We use an API gateway because it centralizes cross-cutting concerns and simplifies the backend services. The reason we chose this architecture is to ensure scalability and fault tolerance. A monolithic architecture would quickly become a bottleneck. Now, let's dive into the core logic, the matching algorithm. This is where most people go wrong. We use a geospatial indexing technique like H3 or S2 to divide the map into cells. We then calculate the distance and ETA between drivers and orders using the Haberstein formula or a more sophisticated routing engine like OSRM. We use a priority queue to rank potential driver matches based on distance, ETA, driver rating, and search pricing. The priority queue ensures we always select the best available driver. Most candidates stop here. Strong answers also address idempotency. Order processing must be idempotent to handle failures. We achieve this by assigning a unique ID to each order and checking for its existence before processing. Your interviewer will push back. Why not just use a simple nearest neighbor search? Because it doesn't scale. Nearest neighbor search becomes computationally expensive with millions of drivers and orders. Geospatial indexing reduces the search space dramatically. What happens if the routing engine fails?
We can fall back to the Haberstein formula as a backup, albeit with less accurate ETAs. Another critical aspect is reconciliation, ensuring that the correct amounts are transferred between the user, the restaurant, and the driver. This requires careful tracking of transactions and handling of disputes. We use two-phase commit to ensure atomicity across multiple services during payment processing. The reason we use H3 is because it provides a hierarchical grid system, allowing for efficient zooming and aggregation of data at different resolutions. Alternatives like quad trees were considered, but H3 offers better performance for our use case. Think of H3 like a zoomable map grid. It lets us quickly narrow down the search for nearby drivers.
Building on the matching algorithm, let's consider the data model. For the database, we'll use Postgres with PostGIS extension for geospatial data because it's ACID compliant and offers robust geospatial support. MongoDB was considered, but its lack of ACID properties makes it unsuitable for financial transactions. Pause and think, what's missing from this schema? Here's the schema: orders table, order ID, user ID, restaurant ID, driver ID, order status, order time, delivery address, delivery lat, delivery long, total amount, payment method, created at, updated at, job ID. We also need a driver's table, driver ID, user ID, current lat, current long, availability status, rating, created at, updated at, and a restaurants table, restaurant ID, name, address, lat, long, menu, created at, updated at. We'll index delivery lat and delivery long in the orders table and current lat and current long in the drivers table for efficient geospatial queries. The job ID field allows us to track asynchronous tasks related to the order.
Now, let's tackle scaling and performance. We'll use caching extensively to reduce database load. Redis will cache frequently accessed restaurant menus and user profiles because it offers low-latency key-value lookups. Memcached was considered, but Redis's richer data structures make it a better fit. We'll implement a cache-aside pattern. For geospatial queries, we can use a geospatial cache like Redis with geohashes. To handle the 6QPS, we'll use read replicas. For higher write throughput, we'll shard the orders table based on restaurant ID or geographical region. Remember the 30% drop-off rate we mentioned in the hook? Caching and sharding help us reduce latency and improve ETA accuracy, directly addressing that issue. Finally, we can use a CDN to serve static content like restaurant images and menu files. An experienced interviewer will probe, what happens at 10x scale? Sharding is the key. Horizontal scaling of the database across multiple shards allows us to handle increasing data volumes and traffic. The trade-off here is increased complexity in managing distributed data. We can also use consistent hashing to distribute data across shards more evenly. Consistent hashing minimizes data movement when adding or removing shards. The reason we use consistent hashing is because it minimizes data redistribution when nodes are added or removed, reducing downtime and improving overall system stability.
With scaling addressed, we need to ensure reliability and smooth operations. For fault tolerance, we'll use multiple availability zones for all services. If one AZ goes down, the others can take over. We'll implement comprehensive monitoring using Prometheus and Grafana to track key metrics like API latency, database performance, and error rates. We'll set up alerting using PagerDuty to notify on-call engineers of critical issues. For example, if API latency exceeds 200 milliseconds, an alert will be triggered. If the database fails, the application will automatically fail over to a read replica. The trade-off here is increased operational overhead. We can also implement circuit breakers to prevent cascading failures. Circuit breakers prevent cascading failures by stopping requests to failing services. The reason we use Prometheus is because it's a pull-based system, allowing us to monitor services without requiring them to push metrics. Alternatives like StatsD were considered, but Prometheus offers better scalability and flexibility.
In summary, we designed a scalable and reliable food delivery platform. Key components include the matching algorithm, real-time location tracking, geospatial data handling, and order management. Trade-offs were made between consistency and availability. We chose eventual consistency for ratings and reviews, but strong consistency for order status. Potential bottlenecks include the matching algorithm and geospatial data handling. Next steps include implementing more advanced features like real-time driver location optimization and predicted ETAs. This is how you design a system that minimizes order abandonment and maximizes efficiency. We also need to consider payment gateway integration, ledger management, transaction service, fraud detection, and an API gateway for a complete system.
Want to master more engineering concepts and coding patterns? Subscribe for weekly tutorials that answer the questions developers face in real interviews and projects. If you found this helpful, please like, share, and subscribe for more technical deep dives like this.